Hi, my name is Emily Hartley, and I am a data analyst at the Critical Path Institute, as are my teammates for this project, Rupal and Kurt. Today, I'm going to talk about our TF-IDF and nearest neighbors approach to the metadata automation dream challenge. We used Python to implement our approach, particularly the scikit-learn and fuzzy wuzzy libraries. At the high level, our algorithm steps included pre-processing the metadata and query files, representing the data as n-grams and TF-IDF vectors, searching for the nearest neighbors, and then the final selection and ranking of the CDE matches. As a first step, we processed the metadata and query files to prepare them for our search algorithm. For the CADSR file, this included filling in missing values, parsing the permissible value field, and grouping the data type values into high-level categories. For the input data file, we inferred the data type categories and the enumeration status of each column. Before I discuss our data representation step, I'm going to give a quick explanation of TF-IDF, which stands for Term Frequency Inverse Document Frequency. TF-IDF measures how important a term is to a specific document within a set of documents. This means that terms that are unique to a single document and therefore can be used to characterize the document have a higher TF-IDF value than terms that commonly occur across all the documents. In the example on the previous slide, whole words were used as the terms in the TF-IDF computations. However, we chose to use bigrams or n-grams of length 2 as our TF-IDF terms instead of whole words, since column names and data files often don't have word boundaries. We created two versions of our n-gram function, one that replaced word boundary characters, such as underscores, with spaces, and one that removed all spaces. We applied these functions to select metadata and query fields to construct the vocabulary of bigrams used in our TF-IDF calculations. Now, to construct the TF-IDF vectors, we use the TF-IDF vectorizer class from scikit-learn. We selected 8 fields from the metadata and applied the vectorizer to each, resulting in a bigram vocabulary for each field and a corresponding TF-IDF vector for each value in the field. Then, we applied the vectorizer to the query fields to construct TF-IDF vectors corresponding to each of the 8 metadata bigram vocabularies. Lastly, we used the column transformer class, also from scikit-learn, on both the metadata and query data to combine the 8 sets of TF-IDF vectors into a single feature space for each. Once we have all the data represented as TF-IDF vectors, we search for the best CDE matches for each column header by using the nearest neighbors class to find 15 CDEs with the smallest distance between the metadata and query TF-IDF vectors. Then, for any returned CDE neighbors that are enumerated, we performed an observed value to permissible value search using the fuzzy wuzzy library. These fuzzy wuzzy scores are used to help rank the 15 CDEs. The final step of our algorithm is to select and rank the 3 results for each query column that will be output in the annotation file. To do this, we followed this decision tree. If all 15 CDEs were non-enumerated, then we rank the results using the TF-IDF distance scores. If all the CDEs were enumerated, we rank the results using the fuzzy wuzzy scores. If the 15 neighbors contain a mixture of enumerated and non-enumerated CDEs, we inferred the enumeration status of the query column. If we determined it was non-enumerated, we followed the non-enumerated branch of the tree. Otherwise, if we determined that the query was enumerated, we used a hybrid approach by selecting the best fuzzy wuzzy score and then the best TF-IDF scores. For each branch of the tree, we compared the TF-IDF and fuzzy wuzzy scores to cutoff values to decide whether no match should be one of the results included in the output annotation file. Overall, our algorithm performed fairly well on the test datasets used for the challenge, but there are still many ways in which it can be improved. For instance, we could utilize a thesaurus to help match acronyms and synonyms that don't have any common bigrams. Also, we could use additional CADSR fields to determine the quality of matches. For additional information about our algorithm, you can view our poster in the virtual poster hall, or you can send me an email. You can also access our code on our Synapse project page. Thank you.